Hey everyone, and welcome to this explainer. Today, we are taking a pretty wild journey. We're going to start from the very small scale of our everyday lives, and then zoom all the way out to the cosmic fabric of space-time, all to really understand the invisible force of gravitation.
Here is our roadmap for today's explainer. We'll start with the universal pull, move on to the rules of the orbit, take a look at Earth's gravitational quirks, bust some myths with the free fall illusion, and finally, look at escaping Earth's grip.
All right, let's jump right into part one, the universal pull, from apples to absolutely everything.
So, we all know the classic story, right? Isaac Newton is observing an apple fall. He notes it drops vertically, straight down toward the center of the Earth. But, the truly fascinating part wasn't the apple itself. He looked up at the moon and had this massive realization. The exact same invisible force pulling that apple down into the dirt might be the very same force pulling the moon into its orbit.
And this brings us right to Newton's universal law of gravitation. It's totally mind-blowing because it means if this force acts on apples and the moon, it must act on everything. Literally everything with mass is pulling on everything else. The bigger the masses, the stronger the pull. But as things get farther apart, that pull drops off incredibly fast, by the square of the distance to be exact.
Now, think about this for a sec. If gravity is truly universal, does that mean you are gravitationally attracting the person sitting right next to you? Like, does your coffee cup have a gravitational pull on your hand?
Well, the answer is actually yes. Let's say two friends, Mahendra and Virat, are sitting exactly 1 meter apart on a bench. Because their masses are just so astronomically small compared to, say, a planet, the gravitational force between them is a ridiculously tiny number. We're talking just over 4/10,000,000ths of a Newton. It's so weak that just the simple friction of sitting on the bench easily stops them from sliding right into each other. Moving on to part two, rules of the orbit, the cosmic relay race.
So if everything is pulling on everything else, why don't planets just crash straight into the sun? Well, before Newton even wrote down his equations, a brilliant astronomer named Johannes Kepler gathered these massive amounts of naked-eye data. Kepler essentially spent his time trying to figure out exactly what the planets were doing. Then he basically passed the baton to Newton, who used Kepler's detailed observations to mathematically figure out why they were doing it.
See, Kepler came up with these three beautifully elegant laws describing celestial motion. He showed that planets move in flattened circles called ellipses, and that they actually change speeds. They move faster when they're closer to the sun, so they sweep out equal areas in equal times. But remember, Kepler had absolutely no idea what physical force was causing this elaborate dance.
It was Newton who solved Kepler's mystery by conceptualizing centripetal or center-seeking force. Think about it like this. If you tie a stone to a string and swing it around, you have to constantly pull inward to keep it moving in a circle, right? If you let go, it just flies off in a straight line. Gravity is basically that invisible string. The sun is constantly pulling inward on the planets, curving their straight-line paths into stable orbits.
Okay, on to part three, Earth's gravitational quirks, the not-so-constant constant.
Bringing things back down to Earth for a minute, our home planet's gravity actually has some highly visible quirks. For instance, the moon's gravity isn't just a one-way street that keeps it in orbit. It actively pulls back on Earth. It pulls the water on Earth directly under it upwards, creating a bulge. And as the Earth rotates, this gravitational stretching creates the high and low tides we see at the beach every single day.
We usually just assume Earth's gravity, denoted as g, is this strict constant of 9.8 meters per second squared, but honestly, it really isn't. Because gravity weakens with distance, g drops significantly the higher up you go. Look at this. By the time you reach a communications satellite, g is merely 0.225. It even changes on the surface, depending on whether you're standing at the bulging equator or the slightly flattened poles.
That brings us to part four, the free fall illusion, where we'll be busting some pretty major gravity myths. Now that we know gravity actually changes depending on where you are, we really need to look at what it actually means to weigh something. We mix up mass and weight all the time in everyday conversation, but scientifically, they're totally different. Your mass is just the amount of matter inside you. That's exactly the same whether you're on Earth, Mars, or floating in deep space. Your weight, however, is literally just the localized force of gravity acting upon that mass. So, if gravity changes, your weight changes. So, Let's say you take a trip to the moon. Your mass doesn't change one bit, but because the moon has a smaller mass and radius than Earth, its gravitational pull is only 1/6 of ours. Your weight drops drastically. Which means if you tried to jump on the moon using the exact same effort you use here on Earth, you'd soar 6 times higher. No way, right?
Now here's a really mind-bending truth about falling objects. If we completely remove air friction, gravity accelerates all falling masses at the exact same rate. It does not matter if you drop a heavy iron ball or a light feather in a vacuum, they will hit the ground at the exact same time. It's a crazy concept that Galileo supposedly proved centuries ago at the Leaning Tower of Pisa.
This specific scenario, moving downwards under the influence of gravity alone, without any other forces pushing or pulling you, is formally called free fall. And understanding what free fall really is brings us to one of the absolute biggest misconceptions in all of physics.
You know when you see astronauts floating around inside the International Space Station, it's so easy to think they are just in zero gravity. But actually, scratch that. Gravity up there is still about 89% as strong as it is down here on the surface. They appear weightless because they are in a constant state of free fall. They're moving horizontally so incredibly fast that as they fall downwards, the Earth just continuously curves away beneath them. They are, quite literally, perpetually falling around the planet.
Finally, Part 5, Escaping Earth's Grip, Breaking Free Forever.
So, if satellites are just perpetually falling towards Earth, how do we ever manage to send probes to places like Mars? Well, overcoming this pull is all about the conservation of energy. Think about throwing a ball straight up in the air. Gravity slows it down until it stops and it falls back. But if you throw it harder, increasing its initial kinetic energy, it fights gravity longer and goes higher. If you just continuously increase that initial vertical velocity, you will eventually hit a mathematical point where the object has enough energy to overcome Earth's gravitational pull entirely. It'll just never fall back.
This sort of magical energetic threshold is called escape velocity. For Earth, an object has to travel vertically at a staggering 11.2 kilometers per second just to break free. That is exactly why we need such massive, powerful rockets to launch interplanetary probes. In contrast, escaping the moon requires way less energy, just 2.37 kilometers per second, all thanks to its much weaker gravitational grip.
But you know, as we zoom out to the wider cosmos, we start to realize that gravity is so much more than just a pull acting at a distance. Back in 1916, Albert Einstein predicted that extreme gravitational events could actually create physical waves. And exactly 100 years later, the LIGO observatories actually detected them, proving once and for all that gravity creates literal ripples across the very fabric of space-time itself.
Which leaves us with a really fascinating thought to ponder as we wrap up this explainer. If a force as common as an apple falling from a tree is actually the result of the curving and rippling of the very fabric of the universe, what other invisible cosmic wonders are we interacting with right now, completely unaware? Keep questioning, keep looking up, and I'll catch you in the next explainer.